Hi guys. I'm just giving you a few slides to help with chapter 6 and chapter 7. Important to work through the notes. This is just auxiliary support to understand the notes better. So an anaerobic digester is really a complex thing. It is, if we have a look at a real digester, there'll be zones of different densities, even if you mix with depth. There's a lot of solids in there. We are really simplifying the reaction. We are assuming that, in a sense, all the solids are dissolved in a liquid concentration. So the solids are slowly getting smaller, but we consider that as almost a dissolved concentration that gets less. Okay, so we do a big simplification of a complex reactor scheme. Important to keep that in mind. Now, just have a look at the overall reaction. Some of you struggle to specifically understand the R relationship to S. Okay, so please, S, people, is dead biomass, and X is the microbial biomass that's alive and that's doing all the work. It's consuming the S, it's growing, and in consuming X, it is making methane, CO2, water, and ammonia. These are like products, you can almost say waste products from generating energy. Now, R, in a sense, R is part of S. It's really the part of S that's not getting converted. But we almost look at it, because the formula here between S and R is different, we are saying that S is converted. One of the products of S is R. Okay, even though it's the R itself is not getting the molecules, or sorry, the atoms aren't getting rearranged, we can consider it as an overall reaction where R is, in a sense, a product. Keep that in mind. With our spec, we will always specify how much of the S is not digestible, and this will influence the amount of methane we make, etc. Okay, so please guys, from chapter 6, there's two reactions. You can see that we're solving for the rate of the first stoichiometry and the rate of the second stoichiometry. Then we add them together because of that death rate. The biomass dies, and as it dies, it forms more methane and CO2. So some of these components like cells, methane, and CO2 will have a contribution from both reactions. So it is an overall reaction. Very important to understand that Rx will now be the mu, that's effectively mu over there, and that will be mu D. Very important. So the problem with modeling the liquid phase is that we're making gases, methane and CO2, and they escape. So we treat them slightly differently because we are interested in the concentration change in the reactor, but we're also interested in the amount of gas that we're making. So when we look at the two gas components, what we do is we return not dCdS, dCdt, but rather dNdt. That's why we multiply with a volume that will be a known quantity in your notes. So please note that the fermentation equation will always contain concentrations, except when it comes to the gases. It will actually, the integration will give you the molar amounts. Therefore, the differential or the fermentation equation will give you the dNdt. Very important that you see the difference. So this will result in plotting the concentrations of the stuff that stays in the liquid, and a separate plot for moles, because we are effectively, from our solve IVP integration, we get moles and not concentration of the two gases. Very important. Of course, the ratio between methane and CO2 is important because that's the quality of your gas. Now, very important, this little two-liner is always used because we want to see what the rates were for the answers. We have a generic function for rate, but now we generated from that function the concentration and molar profiles, and now we are interested in seeing what the rates look like for the answer. So this is really just using the answer, okay? Accordingly, that would be the answer from the integration, and we pass that answers to the response function just in order to know what the rates are at different times in that batch reaction. Okay, so that's very useful. For example, over here, you can see I'm extracting from the rates now the biomass rates, and you can see what happened in this fermentation. It ran at the maximum and then it started decreasing. Why did this decrease happen? Well, I think in this function, only CS actually influenced mu. That was because CS got small and therefore mu, or the overall Rx really, this is Rx, which is mu minus mu d, got small. Important to note that. Okay. When we get to continuous equations, this is now for the non-steady state simulation. It looks very similar. The fermentation equation looks very similar, except that it has this in and outlet term for each of the components. So please distinguish between your feed concentrations and your concentrations in the reactor. So these equations are now similar to the batch equations, except for the in and the out term that got added. And because the in and the out term got added, it's of course a whole new integration. Whenever you're integrating the continuous setup, you'll always have a transient phase followed by a steady state phase. You can see there's changes over here. It's transient, it's transitioning from one starting condition to a place where everything stabilized, that's steady state. So please understand that there's always a transient and then steady state follows with time. Please note that when we're only interested in steady state, we use the F-solve, it's an algebraic solver, and we're really just solving for what's happening at steady state. So we know nothing about the path of getting there. That's the dynamic simulation that you can also do, but we'll always check that this dynamic answer at steady state is the same as the F-solve answer. Important. Okay. So when you have to set up your own fermentation equation in chapter 7 for the steady state, you will see here that I have not included the gases. You don't have to include the gases. You're going to struggle if you include the gases, because the gases, there's no accumulation. They just escape. So when you do the CSTR or the chemostat or the continuous reactor that you want to solve for the steady state, you only have to look at the components that's in the liquid, and that will be stuff like substrate, cells, ammonia, and the recalcitrant fraction. Okay. Please note in the answers from those dynamic simulations, so typically you can solve for a steady state, and you'll see in the tutorial now I'm changing the conditions. If you suddenly change the conditions, you can use the previous steady state as the C0, or the initial concentration starting value, and then because the conditions are different, it won't stay there, it will move. You can see there's movement happening, a transient phase, followed by, well, this one's not fully at steady state, but it's approaching steady state. Very important that you know that we're moving from one steady state, condition change, and then we move to another steady state. Okay, so I've spoken about this. Gases in steady state, we will only include the components that are in the mixture. So make sure you understand these equations. For the fermentation equation at steady state, there won't be a time value. I've just chosen, you don't have to, but I've just chosen to assign the dilution rate as well, so that you can change it when calling upon the function. Okay. Very important, towards the end of chapter 7's tutorial, you're going to solve for a locus plot. So you're going to vary D and get the steady state answers at different Ds. Okay, this is called the locus, and it is not a trajectory. A trajectory is something that you follow. So this is the trajectory plot we have. Before we had a steady state and we moved to a new steady state. And you know, it's very important to understand that a trajectory is the concentration as time goes by. So you're moving from the blue dots to the blue and red dots. Okay, similar over here, you're moving from the blue dots to the blue and red dots. Okay, but please note that this line, actually a locus plot should rather be given by points as opposed to a line, because a line is confusing. You are thinking along the lines of, I move from year to year, but you don't move. That's not your profile. This is your profile. I think these two don't match exactly, but it's just the principle that applies. So each set of solutions, free solutions in this case, is for a specific D. You have to run the reactor to get to a new steady state to find for a different condition the steady state values. So never think, whenever you have D on your x-axis, never think along the lines of, I move from there to there via this concentration change. That's not what's going to happen. This is not the transient. This is not what happens with time. These are other steady state solutions that you're not getting because of your condition change. It's so crucial to understand the difference between a trajectory, a line you follow, and a locus, which is really just given answers at given conditions. They don't move. You don't move along these lines. Very important. Okay, and then lastly, remember that your chemostat or the continuous reactor is very, you can say it's very nice because you can now you can completely control the growth rate. So basically, the rate of cell production is equal to D. Okay, it's as simple as that. In this case, it's not just mu. There's a def rate as well. So it's just the difference between mu and mu D will always be D, and D is something that you set. You set it. It's a condition, and that will then be equal to R8. Keep this in mind when you go through your TUTs. It's a good TUT, good for insight, good for building mathematical insight, but also understanding the basics of how anaerobic digester work. Good luck. We'll talk about this in class.